Kinematics is the study of motion. Rotational kinematics then would describe how something is rotating in terms of rotational motion descriptors. So, looking at a circular system such as this, let's imagine that we had an object out here on the end of some radius r away from the central circle. If I then move this object around in a rotational way from one position to another, we would describe this arc length as lowercase l. This arc length L is swept out during a period in which theta is moved across for the rotational system. Something new here in rotational kinematics is that we are measuring this now in radians as opposed to degrees. In terms of theta, radians then, theta is described as the proportion of length to radius, L divided by R. In this sense, 1 radian is when L equals R. Based on this information, we know that an entire circle has a circumference where L is equal to 2 pi times R. So we can imagine that if theta is equal to 2 pi r, the entire circle, divided by the radius, then this comes out as 2 pi radians. This is where we get the idea that a complete circle is 2 pi and therefore would be equal to 360 degrees, which is where we get our conversion factor between radians and degrees. So therefore, doing the division, we know that 1 radian is equal to 57.3 degrees. Now, really, that's only relevant if we need to convert. And for most of our problems, we'll be working in degrees. But here in the rotational kinematics section, we have to describe this in terms of radians so that we can look at it in terms of theta. There's a few characteristics in addition to just the angle and the distances. Of course, if I pushed on this system and it began to spin, naturally, it would have an angular velocity. That angular velocity would be this spinning. Now, this is not the same as our v, our tangential velocity that we had when we were looking at uniform circular motion, because this velocity is a curve describing how this thing is rotating around. This is called angular velocity and is given the Greek symbol lowercase omega as its characteristic variable. So omega is the rotational rate an object spins, right? And so we can imagine that a certain amount of angle is swept out in time, which is exactly how omega is described. Omega is described as the change in theta in a period of time. Going through the analysis then with the above information up here, we know that omega then would be equal to theta, which would be L over R divided by time. And so if we separate this a little bit and we say that 1 over r times L over t is equal to theta, then we see that really distance divided by time in terms of a rotational rate is our linear speed. And so what this is v, our tangential velocity, divided by the radius. So pulling that all together, we see that omega is equal to the tangential velocity divided by the radius, v over r. Another way to say this would be that our tangential velocity is equal to radius times our angular velocity, omega. This angular velocity, omega, would be measured as a radians per second unit. Obviously, if I then multiply radians per second times a radius, I get meters per second. Similarly, if I had a system such as this, and it was spinning with some angular velocity, and then I increased that velocity, in other words, I spun it faster and faster and faster and faster, we would say that the angular velocity is increasing in time. Well, this would be an acceleration. And so we can measure angular acceleration as a function of angular velocity. Angular acceleration is given the Greek symbol alpha and is described as exactly that, the change in omega in a period of time. Using the above formula, we can simplify this to put it in terms of our tangential velocity, where this would be the change in velocity divided by the radius times the time, and then just separating this into 1 over r times the change in velocity divided by time, we see that this is really acceleration divided by radius. Acceleration as the tangential acceleration, or the straight linear acceleration over r. So we see that alpha is equal to our linear acceleration divided by r, measured in radians per second squared. Or another way to say this is that our linear acceleration is equal to radius times our angular acceleration. Now, we haven't talked too seriously on our circular motion characteristics, so I want to make sure we have this clear. This is our circle. The object at this point is now accelerating this way, which we've already seen as our centripetal acceleration, AC. So if we had a circular system that, as we saw above, at this position we've already studied that this would have a centripetal acceleration focused towards the center. But now, if I'm pushing on this and causing this to spin faster and faster and faster, then I'm also accelerating it tangentially this way. That is that A that we're describing right here, right? This linear A is a straight line vector that is tangential to the path along the same direction as the velocity, right? But this direction changes depending on where I am along the circle. The centripetal acceleration always angles towards the center. So now it's possible to have a system where I'm not just experiencing a centripetal pull towards the center, but I'm also speeding up or slowing down in terms of the rotational rate. If I track through the variables that we've just solved, then I can also describe centripetal acceleration in terms of angular kinematics, which is our friend from uniform circular motion, A sub c. Right? Centripetal acceleration is acting towards the center. We've already seen that centripetal acceleration is our linear velocity squared divided by the radius. Putting v in terms of omega as r times omega, then we see that the centripetal acceleration is equal to r times omega, then squared divided by the radius. So of course, r squared omega squared over r reduces to omega squared times the radius. So the centripetal acceleration is equal to omega squared times your radius. Each one of these will be valuable information when we talk about causing an object to speed up or slow down. In other words, beginning to turn or stopping turning over time.